Hi, I am Sanjay Patel. In this video, we are going to discuss convergence of a special series which is known as the P series. Let us understand what is a P series. A series of the form, sigma 1 upon n raised to p, where n is equal to 1 to infinity, which you can also write in that expanded form 1 upon 1 raised to p plus 1 upon 2 raised to p plus 1 upon 3 raised to p and so on. A series of the form 1 sigma 1 upon n raised to p is called a P series. Here this p is some real number, it is some constant, it is fixed. Okay. For example, suppose if I take p is equal to 1, if you take p is equal to 1, then we get sigma 1 upon n raised to 1. That is sigma 1 upon n, where n is equal to 1 to infinity. So this series is known to us. We have discussed the convergence of this series in our previous videos. And we know that this series is divergent. Okay. Another thing is, suppose if I take p is equal to 2, then the p series will be 1 upon n square, where n is equal to 1 to infinity. So that is 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square and so on. When p is equal to say minus 3, what we get is sigma 1 upon n raised to minus 3, n is equal to 1 to infinity. That also we can write as sigma 1 of sigma n raised to 3, the sigma n cube, where n is equal to 1 to infinity. That is 1 cube plus 2 cube plus 3 cube and so on. So this is also another example of P series. P can be any real number. Suppose if I take P is equal to 1 by 2, then I will get sigma n is equal to 1 to infinity 1 upon n raised to 1 by 2. That is sigma 1 upon root n, and that we can write as say 1 upon root 1 plus 1 upon root 2 plus 1 upon root 3 and so on. Okay, so these are the examples of P series, and now we are interested in discussion of for which values of this P that this series will be convergent. Okay, so what are the conditions on the number p so that sigma 1 upon n raised to p is convergent? So we'll prove a theorem which is very, very important. With the help of this theorem, we can determine some special type of series are convergent or not. Okay, so let us prove this theorem. Okay, so the theorem is it is called P series test. We'll call it P series test. This theorem tells the P series sigma 1 upon n raised to p, where n is equal to 1 to infinity, is number 1 is convergent if the value of p is greater than 1, and it is divergent if the value of the constant p is less than or equal to 1. Remember that p is any real number here. Okay, so let us prove this. First we'll consider the case 1, where we assume that the value of p is greater than 1. So in this case, we must show that the series sigma 1 upon n raised to p is convergent. So suppose p is greater than 1. And our series in this case is given by, say, sigma 1 upon n raised to p, n is equal to 1 to infinity, is 1 upon 1 raised to p plus 1 upon 2 raised to p. Let me write down some more terms. to understand the logic of these arguments. 4 raised to p plus 1 upon 5 raised to p, 6 raised to p, 1 upon 7 raised to p, and so on. Okay. Now, I want to make groups of different terms. Say first I will take only one term, this term, first term, and then I will take two terms, the next two terms. Then I will take next four terms, that is this. So first I am taking one term, then two terms, then four terms. So this is 2 raised to 1 term, then I will taking 2 raised to 2 terms, and then the next what we are going to do is we'll take say 2 raised to 3, that is 8 terms. Okay, 8 terms, and then 2 raised to 4, 16. Okay. Likewise, we continue this. Then we can write this series in this way. So first 1 upon 1 raised to p plus 1 upon 2 raised to p. This is the second bracket or the second group. Then I am taking 1 upon 4 raised to p plus 1 upon 5 raised to p plus 6 raised to p plus 1 upon 7 raised to p. Now what will be the next? The next contains 2 cube, that is 8 terms. So it will be starting with 1 upon 8 raised to p, then 1 upon 9 raised to p, up to, what will be the last term? It is 1 upon 15 raised to p. Okay. And the next we will start with 1 upon 16 raised to p and so on. So you observe that this here it is 1 term, 2 terms, 4 terms, 8 terms. Okay. And so on. Now, I will keep the first term as it is, say 1 upon 1 raised to p, okay, in the first bracket. In the second bracket, there are two numbers, 1 upon 2 raised to p and 1 upon 3 raised to p, and I will replace all the numbers by the largest number. What is the largest number between 1 upon 2 raised to p and 1 upon 3 raised to p? It is 1 upon 2 raised to p, since p is greater than 1. So if I replace all the numbers other than this 2 raised to p by 1 upon 2 raised to p, what I will get is this sum is less than 1 upon 2 raised to p plus 1 upon 2 raised to p. This can be proved very easily why this sum is less than this. And just for simplicity, we are understanding in a simple direct way. In this third bracket, there are 4 terms. Among all these 4 terms, this 1 upon 4 raised to p, 1 upon 4 raised to p is the largest one, because as the denominator is smallest, the value of the fraction is the, say, largest. Here 5, 6, 7 are more, and p is also greater than 1. That is also very, very important. So if I replace all these numbers, 1 upon 5 raised to 6, 1 upon 6 raised to, 1 upon 5 raised to p, 1 upon 6 raised to p plus 1 upon 7 raised to p by 1 upon 4 raised to p, then this sum is less than, again, by 1 upon 4 raised to p plus 1 upon 4 raised to p plus 1 upon 4 raised to p plus 1 upon 4 raised to p. Each of this number is less than 1 upon 4 raised to p. Same way in the last bracket, or rather in this fourth bracket, I want to replace all the numbers by the largest one, that is 1 upon 8 raised to p is the largest here. So this sum is less than 1 upon 8 raised to p plus 1 upon 8 raised to p, and that is how many times? You know there are 8 terms here, so this is 8 times. So in next bracket, you will have 1 upon 16 raised to p plus 1 upon 16 raised to p, and that will be, say, 16 times, and so on. Okay, so let us simplify this. If you simplify, what you will get is this is equal to 1 upon 1 raised to p plus, this is 2 times 1 upon 2 raised to p. This is 1 upon 4 raised to p plus 1 upon 4 raised to p 4 times. So 4 times 4 times 1 upon 4 raised to p, then 8 times, this bracket contains 8 1 upon 8 raised to p. So 8 times 1 upon 8 raised to p, then 16 times 1 upon 16 raised to p, and so on. So up to infinite terms. Okay. Now this we can further simplify and write it as 1 upon 1 raised to p plus 1 upon 2 raised to p minus 1. This is 2 square upon 2 raised to 2p. Okay, then this is 2 cube upon 2 raised to 3p. This is 2 raised to 4 upon 2 raised to 4p, and so on. So again we are writing this as 1 upon 1 raised to p plus 1 upon 2 raised to p minus 1. This becomes 1 upon 2 raised to 2p minus 2, that is 1 upon 2 raised to 2 times p minus 1 plus 1 upon 2 raised to 3 times p minus 1 plus 1 upon 2 raised to 4 times p minus 1, and so on. Okay. Now you can observe that this is a familiar series, and that series is actually the geometric series. Why it is geometric series? Because if you check the ratio of the two successive terms, say if you take this upon this, the third term upon the second term, the ratio is 1 upon 2 raised to p minus 1. For example, say the third term is 1 upon 2 raised to 2 into p minus 1. This divided by 1 upon 2 raised to p minus 1. That gives you 1 upon 2 raised to p minus 1. Okay. So second term upon first term, third term upon second term, fourth upon third, and so on. The ratio will be the same, that is 1 upon 2 raised to p minus 1. So this is a geometric series with the first term 1, and the common ratio is say r is equal to 1 upon 2 raised to p minus 1. Okay. Let me just write this as the result number 1. Let's remove this. Okay. Now, the RHS series, the RHS of 1, the data inside of this result number 1, is a geometric series, with the first term, as a is equal to say 1, and the common ratio r is equal to 1 upon 2 raised to p minus 1. So this is very, very important. And now we see what is the condition on r. As we have p is greater than 1, we can see that p minus 1 is greater than 0. Okay, and we know that if p minus 1 is greater than 0, then 2 raised to p minus 1 is greater than 2 raised to 0, that is 1, because a raised to x is increasing function when a is say greater than 1. A raised to x is increasing if a is greater than 1. So the base value is 2, so it is greater than 1, and therefore whenever x is greater than y, a raised to x is greater than a raised to y. So that gives us 2 raised to p minus 1 is greater than 1, and that means 1 upon 2 raised to p minus 1 is less than 1 upon 1, that is 1. Also, this 1 upon 2 raised to p minus 1 value is positive. So what we get is 0 is less than 1 upon 2 raised to p minus 1 is less than 1. So that is the ratio r is lying between 0 and 1. So since the ratio is between 0 and 1, this geometric series in 1 is convergent. This series is convergent. So let me write hence the series on the RHS of result 1 is convergent, and not the end, the sum is given by a upon 1 minus r. What is a here? For this series, the first term is 1 upon 1 raised to p, that is 1, and the common ratio is r is equal to 1 upon 2 raised to p minus 1. So putting these values, we will get the sum of this series as 1 upon 1 minus 1 upon 2 raised to p minus 1. Okay, and this series, this sum is some finite real number because everything is fixed. So this is some finite real number. This is some finite real number. So what we have proved is this. Therefore, the left hand side series, see result number 1. What we have proved is sigma 1 upon n raised to p, which is our left hand side series, is less than this sum. And this sum is finite. And this sum, sigma 1 upon n raised to p, is even smaller than this. Therefore, this sum is also finite and it is a real number. And remember, this 1 upon n raised to p is positive, so it is also bounded below by 0. Okay, so I can say, therefore, sigma 1 upon n raised to p, is less than 1 upon 1 raised to p plus 1 upon 2 raised to p plus 1 upon 3 raised to p and so on. This we are writing from result number 1, which is equal to 1 upon 1 minus 1 upon 2 raised to p minus 1. Okay, and since series on LHS, which is less than this number, which is a finite real number, it is a real number. Okay, and therefore this series sigma 1 upon n raised to p, where n is equal to 1 to infinity, is convergent because its sum is also finite. In here we have used the condition that the value of p is greater than 1. So the case 1 is over. Whenever p is greater than 1, what we have proved is this series is convergent. Now let us assume that p is less than or equal to 1 as case 2. Case 2 we will discuss now. Say case 2. Suppose the real number p is less than or equal to 1. Okay, so on this number line, p is less than or equal to 1. Suppose we have 0 here, we have 1 here, and p can be any number which is less than or equal to 1, including 1. Okay, so here I am going to consider different cases. What about what happens when p is equal to 1? What happens when p is between 0 and 1? And what happens when p is less than 0? Okay, so let us discuss this sub cases here. So first, in this case, suppose p is say less than 0. If p is less than 0, okay, then we have limit n tends to infinity. We have limit n tends to infinity of say 1 upon n raised to p. 1 upon n raised to p, that is limit n tends to infinity n raised to minus p. This tends to infinity because minus p is positive. As p is less than 0, we have minus p is greater than 0. So this is some positive power, and n keeps on increasing, and its positive raised to positive power is also going to increase indefinitely. So this limit does not exist, and therefore what we have proved here is, in this case, the nth term of this series sigma 1 upon n raised to p tends to infinity. It is not 0. It is not 0, and therefore this is divergent. Okay, I can say this is not equal to 0. Okay? So limit n tends to infinity, an is not equal to 0, then sigma an is convergent. We are using that first theorem. Now number 2, suppose p is equal to 1. Suppose p is equal to 1. This we also proved that for p is equal to 1, the series sigma 1 upon n raised to p will be sigma 1 upon n raised to 1. In this case, sigma 1 upon n raised to p becomes sigma 1 upon n is equal to 1 to infinity. And this convergence we already discussed, but we will write it again here. This is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5, 1 by 6, 1 by 7, and so on. We are writing more terms. to understand the logic. This we can group in this way, the first two terms as it is, then I am taking these two terms, then 5, 6, 7, 8, okay, and then so on. So this is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 and so on. Okay, and this is say greater than, this is greater than 1 plus 1 by 2 as it is. Among these two terms, I want to replace this by the say smallest term, that is 1 upon 4. So this sum 1 by 3 plus 1 by 4 is greater than 1 by 4 plus 1 by 4. Then here in these four numbers, the smallest is 1 upon 8. So I am replacing all numbers by 1 upon 8. The new sum that is 1 upon 8 plus 1 upon 8 plus 1 upon 8, 4 times. This sum is say less than this original sum and so on. So that gives us 1 plus 1 by 2, then 2 times 1 by 4, x plus x is 2x. So 2 times 1 by 4 is 1 by 2. Then 4 times 1 by 8 is again 1 by 2 and so on. So you will get this thing up to infinite terms. Okay, and this tends to infinity. That means this right hand side series sum does not exist. It is infinity. So the left hand side series, which is bigger than this series, is also say converging to infinity, or it is not divergent. It is not convergent. So therefore, sigma 1 upon n is divergent. Okay. So what we have proved is, for the case p is equal to 1, the series sigma 1 upon n raised to p, that is sigma 1 upon n, is divergent. So among these cases, p less than 0 and p is equal to 1 is proved. For p equal to 0, it is also obvious. So case 3, I can say, for p is equal to 0, it is very, very simple. For p equal to 0, what we'll get is sigma 1 upon n raised to p, 1 to infinity, becomes sigma 1 upon n raised to 0, which is nothing but sigma 1 n is equal to 1 to infinity. That is 1 plus 1 plus 1 plus 1 infinite times. Infinite times. Okay. But it is an infinite number of terms like this. So this tends to infinity, and therefore we can say that sigma 1 upon n raised to p is also divergent. Is also divergent for p equal to 0. For p is equal to 0. So what remains for us is to discuss the case for 0 less than p less than 1. Okay. So let us discuss the subcase number 4. Say number 4. Suppose 0 is less than p and p is less than 1. Okay. Now if 0 less than p less than 1 is given, then we know that that n raised to p is always less than n. Okay. And here it is always less than or equal to n, because if n is equal to 1, these two will be equal. Okay, so what I want to exclude n equal to 1. So I can write n raised to p is less than n if n is greater than 1. We can omit a few terms, so that does not change the convergence. Okay, so n raised to p is less than n. So this implies 1 upon n raised to p is greater than 1 upon n. Okay, so this is my say, you can say this is your an, this you can call as bn, and what do we have is an is strictly greater than bn for every n greater than 1. So therefore by comparison test, if sigma Bn is divergent, then sigma An is also divergent. And we know that this series sigma Bn, that is sigma 1 upon n, is divergent. So I can say, therefore, by comparison test, sigma An is divergent, okay, as sigma Bn, that is sigma 1 upon n, which you already proved that it is divergent. By comparison test, because of this condition, sigma An is divergent, because this sum, if we have this condition, say An greater than Bn, and if you keep on adding A1, A2, A3, and similarly, if you keep on adding all these inequalities, then A1 plus A2 plus A3 plus and so on is greater than B1 plus B2 plus B3 and so on. So sigma N is greater than sigma Bn. But sigma Bn is infinity, it is divergent, so sigma N is even more than that, so it is also infinity, or it is divergent. Okay, so in this case, sigma 1 upon n raised to p is divergent if 0 less than p less than 1 is proved for n equal to 1 to infinity. Okay, so we discuss all the cases, and this case 1, 2, 3 and 4 says the final conclusion as, so thus you can say, therefore sigma 1 upon n raised to p, n is equal to 1 to infinity, okay, is divergent for p is less than or equal to 1. So when p equal to 1, p equal to 0, p is less than 0, or 0 less than p less than 1, we discuss all the cases. So hence the theorem is proved. So this is very, very important theorem. Using this theorem, we can discuss convergence of some series by the help of practical comparison test, and that we are going to see in our next lecture. So thank you so much.